Welcome to this EWRB Electrical Service Technician Training course. I'm Aria, an electrical tutor working with Roy. In this course, I'll guide you through all the topics covered in the EWRB Electrical Service Technician Exam Teaching Guidelines. Welcome back. In our last session, we covered Topic 8.3, Power and Energy, where we learned how voltage and current combine to create power and how electrical energy is measured in kilowatt-hours. Now we move on to Topic 8.4, Electrical Conductors. This topic is extremely important for service technicians because every electrical circuit relies on the quality of its conductors. When we say conductor, we mean any material that allows electric current to flow easily. Over the next few minutes, we'll look at the different types of conductors, their properties, the environments they're suited for, and why good connections are essential for safety and long service life. Let's begin with Topic A. Topic A, Properties and Uses of Common Conductors. Electrical conductors come in many forms: flexible, rigid, fine-stranded, or solid. Each is designed for a specific purpose depending on how and where it's used. Let's start with the most common one, copper. Copper is used almost everywhere because it has low resistance, high conductivity, and excellent mechanical strength. It's flexible enough for wiring, yet strong enough to stay tight under terminals. Next is aluminium. Aluminium is lighter and cheaper than copper but has a higher resistance, which means it needs a larger cross-section to carry the same current. It's often used in large distribution cables and overhead lines where weight matters. Then we have silver, which is actually the best natural conductor of electricity. It's used only in specialized equipment like switch contacts or precision instruments because it's expensive. Tungsten and nichrome are used for heating elements. Tungsten has a very high melting point, and nichrome, an alloy of nickel and chromium, resists oxidation and glows red hot without melting. Carbon is used in arc lamps and certain types of motor brushes because it can handle high temperatures and still conduct. Brass and bimetals are used where we need mechanical strength or specific switching behavior, such as in thermostats or circuit breakers. So when we choose a conductor, we must think about how it behaves with heat, moisture, vibration, or chemical exposure, and whether it needs to be flexible or rigid. Topic B. Advantages and disadvantages of common conductor materials. Now let's move on to Topic B, where we compare the advantages and disadvantages of these materials under real-world conditions. Starting with copper again, it's excellent in most situations, but it can oxidize if exposed to moisture or chemicals, so we usually tin plate or insulate it. Copper is also heavy and more expensive than aluminium. Aluminium, on the other hand, is lighter and cheaper, but it forms an oxide layer that increases resistance at joints. That's why aluminium connections must be cleaned and coated with anti-oxidizing compound before tightening. Silver conducts extremely well, resists corrosion, but is too costly for normal wiring. Tungsten has high strength and a very high melting point, making it ideal for lamp filaments, but it's brittle and hard to work with. Nichrome is perfect for heating elements because it can withstand high temperatures without oxidizing, though its resistance is much higher than copper. Carbon conducts poorly compared with metals but tolerates heat and arcing, making it valuable in brushes and arc lighting. So each conductor has a job where its strengths outweigh its weaknesses. In the exam, you may see a question like, which conductor would best suit a heating element exposed to air? The answer would be nichrome, because it handles both heat and oxidation well. Topic C. Importance of secure, well-made connections. Now let's move to Topic C, which focuses on connections. Even if the conductor material is perfect, a poor connection can ruin the entire circuit. Loose, corroded, or poorly terminated joints create resistance points. Resistance means heat, and heat means potential damage, fire, or voltage drop. A well-made connection should be clean, with no dirt or oxidation on the surfaces, tight, but not over-tightened to the point of damaging the strands, correctly crimped or soldered, depending on the connector type. When we join conductors, the joint must carry the same current as the cable itself. If the joint has higher resistance, it becomes a weak point. This is why we use proper crimp lugs, terminal posts, and washers, and why every screw or clamp must be tightened to the right torque. In the field, many faults come down to loose or overheated terminals. A quick inspection or tightening could prevent major failures. So always remember, the safety and service life of a conductor depend not only on its material, but on how well it's connected. Topic D. Selecting suitable conductors for different applications. Now let's move to the final part. Topic D. Choosing the right conductor for each situation. When selecting a conductor, there are several factors to think about. First, the current carrying capacity, also known as ampacity. The conductor must safely carry the expected load without overheating. This depends on its cross-sectional area, the material used, and the installation conditions. Second, the voltage drop. If the conductor is too small or too long, the voltage at the load may be lower than intended, which can cause equipment to run poorly or overheat. Third, the environmental conditions. If the conductor is exposed to heat, moisture, oil, or vibration, we must select the right insulation and sheath type. For example, a flexible lead on a portable tool may use heat-resistant or oil-resistant insulation, while a fixed installation might use TPS cable. Fourth, the mechanical requirements. Flexible cords are used where movement is frequent, for example, power tools, extension leads, or appliances. Rigid cables are used in fixed wiring systems. We also need to consider how the conductor is supported, such as in conduit, trunking, or buried underground. Fifth, cost and availability. Sometimes we balance performance with practicality. Copper is ideal, but for long underground runs or overhead lines, aluminium may be more economical and lighter. Finally, think about safety and compliance. All conductors used in New Zealand must comply with AS/NZS 3000 and AS/NZS 3008.1, which specify current ratings, temperature limits, and installation methods. To give a few examples, flexible cords with a cross-section up to 4 square millimeters are used for portable appliances. Neutral screen cables are used for underground supplies where mechanical protection is needed. MIMS, or mineral insulated metal sheathed cables, are used in areas of high temperature, such as ovens or fire-rated systems. Steel-wired armored cables are used where impact protection is important. Each choice must ensure that the conductor can safely carry the load, resist damage, and last for the lifetime of the installation. Connecting everything together. Now that we've gone through all 4 parts of topic 8.4, let's bring the ideas together. We started by learning about the different types of conductors and their general properties: copper, aluminium, silver, tungsten, nichrome, and others. We compared their advantages and disadvantages under various conditions such as heat, corrosion, and vibration. We discussed how vital it is to have secure, clean, and tight connections, because poor joints cause resistance and overheating. And finally, we learned how to choose the right conductor for the job, considering current capacity, voltage drop, environment, and compliance with New Zealand standards. For an electrical service technician, understanding conductor behavior is essential for safe installation, maintenance, and fault finding. When you know which material to use and how to terminate it properly, you prevent many electrical problems before they happen. In the exam, you might see questions such as: which conductor material is best suited for high-temperature heating elements? What effect does a loose terminal have on current flow? Why is aluminium not always suitable for small appliance leads? Every answer comes back to what we've learned in this topic. Summary. To summarize, conductors carry current, and their performance depends on material, size, and environment. Copper is the most common. Aluminium is lighter but less conductive. Special materials like nichrome or tungsten are used for heating, carbon for brushes, silver for high-quality contacts. Secure, well-made joints prevent overheating and faults. Correct conductor selection ensures safety, efficiency, and compliance with standards. That completes topic 8.4, electrical conductors. In our next session, we'll move on to topic 8.5, electrical insulators, where we'll look at the materials that prevent current flow and protect both people and equipment from electric shock.